Okay, everyone. Sorry for the delays. We're still figuring out bugs with this YouTube streaming. So my name is Alan Hunter. Hopefully you can hear me. And we are going to spend the next hour and a half or so looking at how to run the Genesis software on the FEI Nova. Now, for those of you who are not familiar, if you're watching this later, if you're not familiar with this particular microscope, the Nova is a little bit older FEI dual beam instrument. It has both focused ion beam and the SEM column. And the SEM on this is a pretty high resolution SEM. Definitely resolutions down to around a nanometer spatial resolution. And it's a very good workhorse SEM, even without the FIB. Now, for doing EDS, what you'll find is that the resolution of the SEM is less important than just the usability of the microscope, the stability of the microscope. Typically for EDS, we are limited for spatial resolution by the interaction volume when the electron beam hits the sample. So almost any SEM out there, as long as it's not a tungsten filament SEM, almost any SEM is capable of doing high resolution EDS maps and spectra. So what makes this different, this microscope a little different, is that we're still using a fairly old version of software made by EDAX called Genesis, which all the rest of the microscopes in the lab have moved on to team software. So the setup on the Nova is a little bit different than the other systems. But the basics of EDS detector setup and EDS mapping are all pretty similar. So once you work through the differences in the software, it should be pretty straightforward. Now, I am broadcasting both the views of the Nova user interface right here, and also the support computer screen. And what my plan is once I start up the Genesis software, is I will probably shrink the user interface for the Nova down into the corner somewhere, and we'll focus mainly on the Genesis side. But I am putting up the Nova screen for a while until we get everything set up, just to walk you through the settings. So let's go ahead and get started. The samples have been in the microscope. The system is pumped down, and we should be ready to go. Okay, that is floating on top. I think we might have a little bit of a bug I got to work out here. Okay, there we go. All right, so we're going to turn on the electron beam. Like I said, we do have the FIB, but we don't need it for today. So we're going to go to our SEM quadrant and click beam on. And the samples that I have in the microscope today is I have a semiconductor chip, which I thought might be useful just because it has some kind of small features on it. And then I have the FEI alignment sample, which has some gold nanoparticles on it, has some other easy features to do maps on. So let's go ahead and start with the FEI alignment sample first. So we're going to drive over, and let's just start on this sample. Is pretty easy. This is the tin sphere sample. So I find my sample. First thing we want to do is get in focus. And let's zoom in here a little bit. Right, so we get in focus. We link our working distance. And what we always want to do on the Nova for EDS is we always want to be at 5 millimeter working distance. Every microscope has some working distance where the electron beam and the EDS detector are coincident. And on the Nova, that happens to be at 5 millimeters. So if you want your best count rate for your EDS detector, you want to be right at 5 millimeters. That doesn't mean you can't operate EDS at another working distance, but it won't be optimized. And that's actually it's a fairly simple little experiment to try if you want. is just look at your count rates as you move the sample up and down in working distance, and you'll find that it forms some kind of a peak. And that peak value will be where your sample is right in line with the EDS detector. All right, so we're at 5 millimeters working distance, and we're looking at the tin sphere sample. And just as a starting point, let's just do a regular spectra. So for point spectra, usually spatial resolution is not that critical. I'm going to kick up my voltage. Let's just go up to 20 kV accelerating voltage. And we'll use a fairly intermediate beam current. 0.62 nanoamps should be fine. That should be okay. Let me adjust my focus, my astigmatism. Okay, should be good. And let's, here, let me just move over here so we have an area with and without spheres. Okay, so we've got our SEM roughly set up here, and the last thing that we need to do on the Nova is we need to look at the lens conditions. So the Nova has 3 lens modes on it. We have mode 1, field-free mode, mode 2, immersion mode, which is not allowed to go right now, and mode 3, EDX mode. And on the Nova, if you're going to do relatively low resolution EDS work, you have to remember to use the EDX mode. Otherwise, you're going to get a ton of noise in your spectra, and it won't be useful. And because we have the time today, I'm going to demonstrate what that looks like if you forget to change the lens mode. So, and actually, because I can't go to mode 2, I'm going to, it says I need to be under 18.6 kV. I'm going to drop my kV down just a little bit so that it'll let me use the mode 2 lens, so that I can demonstrate some other things about that. So now we have all 3 of our lens modes available. So let's go over to the Genesis software. What I'm going to do here is let's crop my Nova display, which is, let's see, we want to do a filter. We want to do a crop filter. Okay, so there's our Sem image, and we'll just park this down in the corner. Oh, look at that, there's enough room for both. Okay, so for the software, we're going to start up the software. It's called EDAX Genesis. So over here on the support computer, we're just going to double click on that. Uh-oh, failed to connect. That's not good. All right, so that tells me that there is a communication issue between the Genesis computer and the microscope computer, which we should probably try to fix. Unfortunately, the fix to that involves restarting the microscopes and the servers. So bear with me here. We're going to go ahead and do that because we can't have communication problems for what I'm trying to show you today. So let's close Genesis. And we're going to go, first we're going to shut down the support computer. So we'll just go do a normal system restart, no big deal. And then on the microscope computer, let me say, let's turn off the effect. Filters, we'll turn off the crop filter. Right, so for the microscope filter, we're going to stop the server and the user interface by hitting stop. And once that's stopped, then we'll go ahead and do a normal computer restart on that system as well. Okay, so now that our system is rebooted, then we're going to go to the FEI system control, double click on that, and we'll hit start, and that will restart the server on the microscope. And then my support computer with the Genesis software is rebooted now as well. And let's get that up and running as well. Okay, so we'll go ahead and log in to the Nova. Turn our beam back on. Okay, so let's let me turn on the filter again. Filter, crop it back, close. Okay, so hopefully we're back to where we were. So let's go over and we'll restart Genesis. And hopefully this time we won't get a fail to connect. Otherwise, we could be in trouble for today's session. Okay, that looks good. So just keep that in mind, especially with the Genesis software. If you start up that program and anything at all looks weird, best practice would be to restart the Nova server and restart the both computers, because the communication chain between that computer and the Nova is always a little shaky. And you'll run into more trouble when you start to do the imaging and the mapping and stuff like that. You might be able to just do Spectra, but make it easy on yourself. So here's the software layout for Genesis. Before I get too far into it, I should point out that if you go to Help and you say View User Manual, Genesis has a fairly okay user manual in here. It's not the worst one I've ever seen, but it is useful if you want to read through it. It might save you some questions. We do have copies of that on our FOM server and on our file server. But if you're using on the Nova and you don't know something, I would say take a look at that user manual. It's right there. All right, so in the user interface, Genesis has 5 tabs available on our software. Now, this last tab, these last 2 tabs, the particles and multipoint, I believe those only show up on Genesis software where those are activated by a license. So if you happen to use Genesis somewhere else, they may or may not have those modes. I'm not going to go into particle or multipoint mode today. Those are kind of advanced topics, but I can talk about at least what they do. But the other modes are your spectrum mode, image mode, and maps and lines. And you can change modes by just clicking on the tabs up here and going back and forth through the tabs. We're going to start out in spectrum mode, which this is just used to capture chemical information from wherever the electron beam happens to be sitting. You'll notice there's no Sem image here. There's no way to get a Sem image in this tab. So this mode relies 100% on the Nova user interface to dictate where the beam is going to be sitting. So at the moment, you can see that the beam on the Nova is just scanning over a big area of these are tin balls on carbon. So I would expect that if I take a spectra, I should see a spectra showing carbon and tin. And as I prefaced, I don't have the lens in the right mode, so this is actually not going to work well. So first thing we'll do is let's clear the existing spectra. So I'm going to come up here to the top right and click clear. That clears the spectra. And then I'm going to say collect. And we're looking at our spectrum as it's building here, and it's just this pile of garbage. And this is what you will see on the Nova if you forget to get out of lens mode 1. So the field free mode will cause you this problem. So the only solution is to stop the spectra. So we'll stop, and we will switch lens modes. So let's go back, and I'm assuming that everyone watching this will have a basic understanding of how to operate the Nova software, but just to make sure it's clear, let me show what I'm doing here. So on the Nova software, we're going to go up here to the lens mode, and instead of operating in mode 1 field free mode, we're going to switch to mode 3 EDX mode. So when you do that, it turns on the high resolution electron lens at about 10% power or so. And that lens field from the high resolution immersion lens will act as a filter, and it prevents this garbage signal from getting into the EDS detector. Now you'll notice that your image is a little bit on the dim side, and the reason for that is the lens field, in addition to blocking electrons it blocks electrons basically from going to the X-ray detector, but it also does a good job of blocking electrons going to the Everhart-Thornley detector. So if you want a brighter image, I suggest if you're using mode 3, is switch your detector from the Everhart-Thornley to the TLD detector. And you will get a much, much, much brighter signal, and you'll probably be much happier with the way everything's going. You may find you get a little bit of focus and astigmatism changes as you switch that lens from mode 1 to mode 3. So go ahead and just fix your focus, fix your astigmatism problems as you need. All right. So let's crop this back down and get it out of the way. Hopefully I won't have to do too much more demonstration on the Nova software. All right, so let's go back to Genesis, and we will clear our display, and let's say collect, and let's see what happens now. And okay, great. We're actually getting a real spectra this time, not just a pile of noise. However, the count rate is painfully small. Maybe it's acceptable to you, but so if we look down here on the bottom, we have our statistics for the detector. And right now we're getting 400 counts a second, and the parameter called the dead time percent is running at about 4 or 5. This is pretty bad. If you want to do efficient EDS, especially with mapping, we're looking for count rates on the order of like 5 to 20,000 counts a second or higher. The more modern EDS detectors can go way, way, way above 10,000 counts a second and still operate. Now, how do you get the count rates up, and how do you get the dead time to be where you want it to be? Counts per second is only tunable using your accelerating voltage and your beam current on the SEM. So if I want more count rate, I either need to go to higher higher accelerating voltage, which is going to increase the efficiency of the X-ray generation, giving me more counts, or I have to turn up the beam current, which will give me more X-ray counts. And I don't want to fiddle with the accelerating voltage just yet, so what we're going to do is turn up the beam current. So I'm going to stop my Spectra, and we're going to go to our back to the user interface for the SEM, and instead of using 0.6 nanoamps, let's hop up to something like 2.3 nanoamps. And just to be sure, let's double check our alignment. Yeah, our source tilt's off just a little bit. And we can check our lens alignment just to be sure that we're not really badly aligned. Check focus, check astigmatism. Okay, so now even without recording a spectra, if I come over here and look, my count rates are now up in the order of like 1,500 counts a second. Still not great, but much better than they were. So if I want even more counts, say I want to do a map, I think we should probably head upwards to the 9.2 or the 36 nanoamps. So let's try that. Let's go up to the biggest beam current, the 36 nanoamps, and let's adjust our source tilt, make sure we get the brightest image possible. And now our count rates are on the order of 11,000 counts a second, so much better. However, our image resolution is going to be degraded compared to where it was. All right, so we got 12,000 counts a second or so. So now let's go back, we'll clear our spectra, and we can see that our count rate's good, and our dead time is currently sitting at 30% or so. That's actually a really good value. The dead time percent is important to look at because if that percentage gets too high, you'll start to pick up artifacts in your spectra that will negatively affect your interpretation of your data. How do you control the dead time? Well, you can control the dead time by turning the count rate down or up. However, that's usually not the first thing to look at. The better way to control dead time is a parameter called the amplifier time, which on the Genesis software is this little drop down way up here in the top right where it says amp time, and it's a value given in microseconds. In the software, there are, let's see, 1, 2, 3, 4, 5, 6. There are 6 different amplifier times that you can choose. And if you choose a longer amplifier time, you will get better resolution in your X-ray spectra. And if you choose a shorter amplifier time, you'll get worse resolution in your spectra. However, the dead time will go down as you turn down that amplifier time. So what does that look like? Well, let's try it. So we're at the longest amplifier time right now, the 12.8 microseconds, which is giving us a dead time of about 28, 29%. So let's go ahead and collect the spectra. And again, our count rate's rather high, so we're getting really pretty good signal here. Now, in this particular mode, this will collect the spectra until I tell it to stop. Some of these fields on the right have expandable areas, so if you click these little up-down arrows, you can expand these and look at what parameters are adjustable. In this case, it's giving you the option of typing in the geometric parameters. I wouldn't recommend messing with these because we're not remounting the EDS detector on the chamber, so there's no reason to change any of these values. But the working distance value, that should be coming directly from the microscope software. So that should match what you see down here, you know, the 5.07 millimeters. That should match if it's communicating. So we don't really need to worry about that. In some of the other tabs up here, when we do spectral analysis, you can tell the software to count for a specific amount of time. But for right now, we're not doing that. Okay, so let's hit stop. So here's our spectrum. If I want to expand the spectrum, I can right-click the mouse and drag the mouse, or sorry, left-click the mouse and drag the spectrum to the side. So this allows me to expand the spectra by dragging to the right. And if I click and drag to the left, it allows me to scroll to the right or to the left. There's other shortcuts that involve various aspects of hitting, like the shift key and the control key. So if I hold control and then click and drag to the left, I can shrink the spectrum back down. If I hold, what is it? Yeah, I guess that's the only one that's really important is control. That you can drag up and down to expand or shrink the y-axis. If your display gets really messed up, if you go up here to the top, there's this little house icon, this home icon. This resets your display back to the standard starting point. So if you get really, really messed up, I would say go for that. Some of the other icons up here in the toolbar, the stopwatch is the same thing as hitting the collect button over here on the right. So this is like start and stop Spectra collection. And the little paintbrush roller is actually the eraser icon. That does the same thing as clear. These icons here are also ways to expand and shrink the spectra if you don't want to use the mouse command. And again, you got the home button. All right, so once you have a spectra, most people would want to know, okay, what are these peaks? You can do auto peak ID by coming over here to the right and just simply clicking the peak ID button. So if I do that, let's see what happens. So I click peak ID, and the software does some thinking, and it comes back, and it says these are the peaks that were in the software, as well as what it found. So the calcium isn't, I don't think is here. So let's say delete all, and say OK. And now the peak ID, yeah, for some reason it thinks there's calcium in here. I don't think that's right. So let's not trust the peak ID. Let's try to do this manually. So I'm going to expand the peak ID table. And let's go in here and let's just click on calcium and say delete. And we'll delete all, let's just delete everything. We'll start from scratch. So if I take the mouse and I click on a peak, let's just start with one of the big peaks here, like this one. It's probably the tin. And I click on it, and it says that based on where I clicked in the spectra, that these elemental lines are all possibles. Now, it helps to know something about your sample before you start down this process, because if you don't know anything about it, you might be tempted to pick some of these other elements. But I know that I don't have a lot of these elements in my sample, but I do know I have tin. So if I click on tin, once I do that, the software then shows me the marker lines for all the different elemental transition lines for tin. And I can make a judgment as how well does this pattern match up with my spectra. Now, I think it matches up pretty well, especially if I raise the line up, show up here, tin. Try to adjust these so they match, and I think that fits pretty well. Maybe this main peak is a little short compared to the reference line, but all the rest of them seem to be pretty reasonable here. So if I want to go ahead and add it as tin, I just click on tin and I say add, and now the tin L marker will show up in my element Z list. Now, you can go through and mark all the rest of the transitions. So for instance, this one right here is going to be another one of the tin L beta peak. So I can click on that and say add. And it says the element is already in the list. So the software doesn't really like that. The reason, I believe, is somewhere in here you can tell the software to look at the individual transitions versus just the element. But anyway, tin is already flagged. So that takes care of most of these peaks. And if we look around, if we want to mark the rest of them, if we come in down here and we say, let's mark turn off the alpha line only designation. So now the software puts a flag on all the different tin peaks that are there. So now we can tell that these are all tin, and we don't have to worry about those. However, we're missing peak IDs on this little peak right here and this big peak down here near 0. So let's do this guy. We'll click on it, and the software suggests that any of these elements are possible. And I think from my intuition, this is probably the carbon peak. So I click carbon, and I'm going to say add. So there's our carbon peak. Let's hit our home display and go back and see. So we still have a few more peaks that we need to sort out, mainly this guy right here. So if I click on this one and look at what it says is possible, it says that could be silicon or tantalum or hafnium. Most likely, this is some kind of a artifact peak from the detector itself. So the detector crystal is made out of silicon, and you can get a silicon X-ray generated inside the detector by a fluorescence, and that can cause this kind of thing. There could also be silicon around the sample area that I might be scattering off of. So if I drop my Sem magnification way down, you know, maybe there's a piece of silicon out here somewhere that I'm not aware of. But anyway, I'm just going to go ahead and mark that as silicon, and there we go. So now we've got all our peaks marked, and let's say we want to do quantification. So again, remember, this spectrum is coming from everywhere that the SEM was scanning. But if I, let's close the peak ID window, and if I hit the quant button, the software will pull up its standardless quantification and tells me the approximate composition of what I was scanning on. So it says that I'm about 62 weight percent tin and about 37 weight percent carbon, or you can also look at atomic percents. You see the silicon that's in there is really low. That's why I think it's probably just like some kind of background or noise problem, maybe from the detector. Okay. If you want to save this, all these, I don't think any of these print functions work because we don't have a printer attached. But what I would recommend you do is just copy all of this and do a copy by Windows and then stick it into WordPad or Notepad and then save it that way. You can, I believe, if you go up to File and say Save As and choose the quant, where is it? Maybe it's not in here. There is a way to save this, but to be honest, I don't remember how to do it off the top of my head. I always just copy and paste it to like WordPad or Notepad and do it that way. Anyway, feel free to play around with this stuff. So we hit OK. Where was it going here? Oh, right. So let's say we want to do point analysis of the sample. So let's say we want to look at an actual tin sphere. In the spectrum tab, what we need to do is to move the microscope around and position the beam right on top of one of these features. So let's just zoom in on one of these tin spheres. Let's get the focus a little better because that's pretty awful. All right, so we'll zoom right in on the center, and let's come back over here. We'll clear our spectrum and hit collect. And so I would expect that we'll get a very minimal carbon signal from this because our beam is sitting right on that big tin ball. We do still get a little bit of carbon. Some of that, there might be actually some carbon in there. There might be contamination on the surface. It's hard to say. It could be a lot of things. But our spectrum, for the most part, is just pure tin here. So let's pause our scanning on the SEM. Let's pause our spectrum collection. And now if we run the quant, we see that this particular area comes back as 97.6 weight percent tin. So almost pure tin. You got to be really careful anytime carbon is involved. Carbon is notoriously bad for quantification. So you will usually see a lot more carbon in your result than you think really should be there. So just watch out for that. If you think the carbon is an error, it's always fair to just come in here, delete carbon, and then run the quant again. And this time, it comes back as 99.2 weight percent tin and just a small fraction of silicon. So if you think the carbon's not real, don't mark it. You don't have to mark every peak in your spectra if you think they're artifacts. Okay, so let's say we want to look at the carbon area is going to be the same, the opposite thing, right? So if we park the beam on an area that is relatively void of tin, like this spot, and then clear and run our spectrum, we should get just a carbon peak in our spectrum and no tin. All right, so pretty straightforward. If you want to save these spectra as you acquire them, you can go up here to File, and you can click Save or Save As, and then you can navigate your file path to somewhere. Let's just go make a folder on the our drive, which is going to be in Documents. Here we go. Nova user data. We'll go to my folder so we don't clutter up anything, and we can say New. We'll do this EDS training, and this is going to be carbon.sbc. Now, you do have the choice when you save on what you want to save. So if you click on this down arrow, there are lots of different things you can save. If you click Spectrum File, that will just save this spectrum, and it saves it in this .sbc format. Let's say you want to import this spectrum into some other program. You might choose to save it instead of the SBC file, to save it as a .csv file. That would probably be useful if you're going to import it. If you want to save the image of the spectrum, then choose one of these image formats. So, for instance, if I say save it as the .png file and click Save, if I go look at that folder now, EDS training, we can see I have a very relatively useless picture of the spectra, but I have no spectrum information. So watch out for that one. If you accidentally save your spectra as images, you'll lose the raw data. So what I recommend you do is there is an option in here to do Save As, and there's a spectrum. Maybe it's not in this tab, but one of the other tabs have a value where it saves both the spectrum and an image at the same time, and I would recommend you use that one. So if we say spectrum file, and we call it carbon again, now if we go look in our folder, we have this carbon.sbc file, which is the raw spectrum. So if you want to analyze this later, so say I clear my spectra, I can go to File, I can say Import Spectrum. This is from another tab. I want to say Open, and I can say it's Carbon Spectrum, and open it. And it says, do you want to use the current files or what's on the system? So we want to use the peak list from the file, and say OK. And then here's our saved file. So this would apply to the offline versions of Genesis as well. This is how you open up your saved data. The only other feature in here I didn't really talk about is the background fitting. The background fitting is kind of done automatically for you. You can open up this down menu, and there are ways you can add and subtract manual points into here if you think the background fit's not very good. I'm not going to go into that. That's kind of an advanced thing, advanced topic, and I don't think most users are going to care about this. But check it out in the manual if you want to try this. But right now it's just on the auto method, and we're going to leave it like that. Okay, so that's the crash course in the Spectrum tab. Before I leave here, let me show you what happens. Another common problem on the microscope is if you go to the user interface and you forget to turn off the CCD camera, right? So on the software, the user interface software, we have our chamber camera down here on the right. And if Genesis is functioning correctly, this will pause when you start collecting EDS data. However, if you forget, if it for some reason doesn't turn off, I want to show you what the spectrum looks like so that you're aware of this problem. So if this is live, the light source from this camera interferes significantly with your EDS map. And so if we come back over and look at, let me slide this out of the way again. If we look at our EDS Genesis setup, you can see that our count rate went from about 12,000 counts a second to over 200 counts a second. And that's because it's now being flooded with signal, flooded with photons from that light source. And the dead time went to 100%. And if I try to collect a spectrum, what you'll see is that you just get this massive noise signal down near zero. Now, I probably should have run a different spectrum, not the carbon one. Here, let me zoom back out here again. Oh, so I wasn't paying attention, and the software actually, the software is fighting me here. You see it actually paused the CCD camera again. Let me clear this. We'll hit collect, and then I'll go back over and let's turn on the CCD camera. And now you see, yeah, this is what I was expecting. So you see you get what it looks like almost no counts at all on the EDS detector. However, it's basically getting so many counts that the detector can't even process it, can't even think straight. So don't forget to turn off the chamber camera. This applies, in our lab, this really applies to the TestScan Mirror 3 and the TestScan Rise, because those TestScan user interfaces, they don't necessarily turn off the infrared camera source when you go to do EDS. So you'll run into this problem more often on those tools. All right, so we talked about two problems there. So remember, the CCD camera has to be paused. And remember, you've got to be in mode 3 to do EDS analysis. Now, you also can do this in mode 2. And that we'll get into when we get into the maps. That's really useful for doing high-resolution maps. But do keep in mind that mode 2 also works. All right, let's take a look a little bit with the what happens when you change the amplifier time versus the dead time. So to really exaggerate this, let's go up to 30 kV on the Sem. Let me get this kind of back off to the side there. And at this point, we're going to be just flooding this detector with signal. So 30 kV generates a lot of X-rays. Let me get my beam aligned here. And how about let's move over to another sample that is going to generate more signal. So on this wafer, let's save our position. In case we want to come back here, this is tin balls. Oops. Clicking on the wrong quadrants, getting myself in trouble. Okay, so let's see, that's the gold. There we go. So this sample right here is a big chunk of, I believe it's tungsten foil, but we'll find out what it is. But it's going to generate a pile of X-rays, I'm sure. All right, so we focus on it, we get in focus, let's add our position, and we'll come back over here, and let's just say, what? All right, so what's going on here? I switched it back to mode 1. All right, we gotta go back to mode 3. All right, here we go. So we're getting 58,000 counts a second. This is about the highest count rate that you're going to get on the Nova. Because again, I'm at 30 kV, I'm at the highest beam current, and I'm looking at a fairly heavy metal sample. So if you want to go much higher than this, I would say head over to one of the other microscopes. They have a lot more beam current available, but 50-something thousand counts a second should be just fine. Now, with this really high count rate, you see that our dead time percent is now jumped up to 85%. And what we need to watch out for is that if I collect a spectrum right here, it's very likely that I'm going to start to see artifact peaks. And if we aren't careful, our spectrum quality is going to be really lousy. So let's run our auto peak ID here. And the auto ID failed miserably. It thinks it's strontium. It's not strontium. So let's try to fix that. Let's click on one of these peaks. And it says possibles are gold. Maybe this is gold foil. I thought it was tungsten foil, but maybe it's a piece of gold. We learn something every day. So this peak is showing up as strontium or silicon maybe. To be honest, I don't know if I even trust any of this because this dead time is so high. Let's get the dead time lower, and then we'll see what happens if this shows any better. So let's stop our spectrum collection. And in order to drop the dead time, we need to reduce the amplifier time. So let's just take it down to 1.6, and we see our dead time drops down to 20%. Kind of the magic number we're looking for is about 30%. So if I go to 3.2 microseconds, we're at about 37%. That should be fine, but let's go to the 1.6 just to see what happens. We'll clear our spectrum and we'll hit collect. And now if I click on these peaks, oh look, now I actually get the right peak ID. And that's because the software is actually interpreting it correctly because my dead time is not ridiculous. So just be careful. If your dead time gets really high, you'll start to get all kinds of weird results. And I bet the peak auto ID, let's see. Yep, the peak auto ID works just fine. It pulls up a bunch of tungsten. It says there's mercury in there. I don't know about that. Let's get rid of that. So we got all kinds of tungsten. All these peaks are tungsten. And they're labeled already, and we're good to go. But just to demonstrate that again, if I go back up to the long amplifier time, and I run my sample, look how different the spectrum looks. It's very garbagey. Lots of extra width on these peaks, lots of noise in the background, and if I run the peak auto ID, it totally messes up the peak auto ID. So again, you don't want to have your dead time too high. 85% way too high. Let's drop it down to 6.4. Should have silenced my phone, I guess. Let's see if it'll work at 6.4. So at 6.4, I'm getting 61% dead time. And if I do my peak ID, it's still getting a lot of really weird results in here. You know, it's saying there's sulfur, gold. None of that's real. So let's drop down to the 3.2 and hit collect. And now my dead time is about 37%. If I run peak ID, now I'm starting to get the true signal. So I don't think this mercury is real. This software, for some reason, thinks there's something there that's not. But again, keep your dead time around 30%. Otherwise, you're opening up yourself to a lot of problems in your interpretation of your data, especially if you're going to use the auto ID. All right. Some of you are probably going to ask, what is dead time? If you've never heard about dead time is the ratio between the collecting time of the EDS detector versus the non-collecting time, or the counting time. And so the way this works is that the EDS detectors cannot measure the energy of an X-ray photon while they are collecting X-ray photons. So we have some certain count rate down here, right? Counts per second, which means that's because the photons are coming in discrete photon particles. The detector is going to open up its the window, which it's all electric. It's not really like a shutter or anything open, but the detector opens itself up to. Sorry, there's someone knocking on my door for a second. I'm really sorry about that interruption. Part of the joys of working in the lab, right? You never know who's going to knock on the door. Okay, so we were talking about dead time. The dead time is the ratio between the live counting and the analyzing. So if, let's say the detector has to hypothetically stay open for 1 second, and then an X-ray photon comes in, and the detector will turn itself off and then measure the energy of that photon. And let's say it takes a tenth of a second to measure the energy of the photon, then the dead time would be the tenth of a second divided by the 1 second, which I guess it's like, what, 10%? If your X-ray count rate coming into the detector is extremely high, what it means is that the detector is spending most of its time figuring out the energy of each X-ray photon, and it's spending relatively a small amount of time actually collecting. So in that case, your dead time value becomes very, very, very high, because another way to think of it is that the moment the detector opens up waiting for an X-ray photon, it gets an X-ray photon. And then it has to shut down, measure the energy of that photon, and then open back up and immediately gets another one. So the amount of live time is very small because it's spending a relatively large amount of time measuring the energies of those photons. Whereas if the dead time is very, very low, it means that the detector is sitting around waiting a long time for X-rays to come in. But when an X-ray actually does enter the detector, it's able to process that energy and then go back to waiting, and there's not another X-ray photon coming in right after it. The amplifier time influences the dead time because it controls how long the detector takes to process the energy of each X-ray. So the longer it takes to process the energy of an X-ray photon, that means the higher your dead time is going to be for the same count rate. So that's why the count rate and the dead time are linked in some ways, but you can also control the dead time independent of count rate by changing the amplifier time. Now, some of you might say, well, why not just use the smallest amplifier time that you can? The reason that we need to be careful about this is, let me drop my beam current down a little bit so I'm not going to saturate the detector, because I need to be able to run this at the longest. Let's see, that's 11%. We can go a little higher than that. Let's go to 2.4 nanoamps. Okay, so let's see what happens to the spectrum as we run it. So we're running right now at the 12.8 microseconds. And we'll just collect a few counts here. And let's zoom in at this peak at all right, so let's look at this peak at the 8.4. The width of that peak, if I measure it using the 12.8 microseconds, is, I don't know, let's just look down here at the base and we'll just ballpark it. It looks like it's about maybe 0.3, I don't know, 0.3 something, maybe 0.4 electron volts wide at the base. And normally you'd measure peak width up here at like full width at half max or something, but I'm not going to do that right now. But just keep that in mind. So we're about somewhere between 0.3 and 0.4 EV wide here. Let's change our amplifier now to the extreme. Let's go down to the 0.5 microseconds, and we'll hit collect. And that's not doing what I thought it would do. It should be fatter. Maybe that one is not, is kind of extreme. All right, maybe the base is a bad part to measure this on. there is the better way probably to do this would be, let's go find the copper sample, and we can do it for real. Okay, so we're now on a different sample. This is going to be the TEM grid. It's copper and aluminum. So this is used for calibrating the detector. And the way we would do this is you set it up so that about half of the field of view is aluminum, about half is copper. And we go in here and we say select PID copper aluminum. All right, and we want a little bit more of the copper signal, so let's move in this way a little bit. Yeah, that looks good. So we got about even heights between the copper and the aluminum peaks. Now, in the calibration, which is setup, calibration, this is done for each individual amplifier time. So let's run it for the really fast one. And the only reason I'm doing this is because it's going to measure the peak width for me. So let's hit start. And the software is going to collect the spectrum, and it's going to tune the detector, but it's going to read back our resolution right here. Let me stop that because I don't want to run 8,000 counts. Let's run like 2,000 counts. Because it's going to take forever. Now I don't think we need 8,000 counts. This is the procedure to do if if the peaks aren't landing where you think they should. This would be the way to fix it. So. Okay, so that calibration ran through, and it says that our resolution with the 0.5 microseconds is 140. So that's a way of measuring resolution. I believe that's a full width half max of a simulated peak. It's not the actual width of these peaks. I think they use the width of this, and then they calculate what the width would be if you were looking at another element. I think it's molybdenum. I might be wrong on that. All right, so let's go and let's see what it looks like. So remember the 140.3. Let's go look at it at the 12.8, and we'll say start. And we should see a better resolution with this condition. I guess my demonstration is falling apart because the resolution is actually worse, slightly. Interesting. So the resolution on this one is 144, and the resolution on this one is 140. Let's try one of the ones in the middle. Let's see. Let's get a more beam current so this doesn't take forever. So that's 130. This is making sense to me. So the resolution's getting smaller as I'm going up in amplifier time. I don't know why the The big one was worse. Yeah, 126. Maybe it doesn't need to be the higher counts. Maybe it's getting affected by noise. Well, I'm not sure what's going on here. Everything that I know about these detectors says the longer amplifier time should have the best resolution, but I'm not really sure what's going on here. Anyway, the takeaway from this demonstration is check your amplifier time and make sure your dead time's not getting ridiculous, because if that happens, you will run into problems with, especially with the auto peak ID functions and that type of problem. All right, so let's get out of this. So let's now take a look at what's probably more interesting is going to be mapping. So let's go back to the tin ball sample. And let's go back down to our smaller voltage. Let's go to 10 kV. Let's start at 10 kV. Why not? And we're going to be using a reasonable beam current. Let's try 8.4 nanoamps to make sure our image looks halfway decent. Do our source tilt. Do lens align because our image quality actually matters now. All right. So let's say here's our image, and say someone comes to me and says, I want to know what's the spectrum on the tin ball and what's the spectrum over here in the carbon, right? So I already showed you one way to do that. You can simply just zoom into both areas and record the spectrum. But let's use it using the image tab. So we're going to click Image in our Genesis software. And now the Image tab has the ability to collect spectra, just like the Spectrum tab, but it also adds the ability to collect SEM images, and then we can use that to guide where our analysis goes. So to collect the SEM image, we're going to go up here and we're going to click Collect Image. Now when you do that, hopefully you can see that the SEM has now gone into external scan mode, which means that the Genesis software is controlling the beam position of the system. And that external will stay on all until you shut it off in Genesis. And the way you do that is there's a little toolbar button up here where it says EXTXY. So if you want to get control back in the Nova software, you click that button, and that gives you control back, so then you can move on to another area. If you want to change the conditions that the electron beam image is acquired with, it's not very intuitive, but you're going to right-click the mouse up here, and when you do that, it gives you the control over these various fields. So you have image resolution. The strips function is something like a line integration feature. So the more strips you do, the better quality this image will be. So if I do like one strip and say collect image, I think this image will be kind of lousy. Actually, it's not terrible. If I do, let's do more. You see, it's sort of like a scan speed. So like the more strips you do, the slower the scan will go. You can look at these things. These are just like readings of the image intensity of the various images you've acquired. So I don't exactly remember how all this works. A lot of it's in the user manual, but this is functions that I've never used. You can hit auto scale, and it'll do like an auto brightness contrast on the image. I don't know if you can tell, but my contrast and brightness are a little different between the live image and the Genesis image. You can also apply lookup tables to this value. So as you click through the lookup table, it kind of does some adjustments to the brightness and contrast. You know, you can play around with some of this stuff and try to have it change the image. I personally just leave it alone. I go with the auto scale. It's probably fine. And then you can save these images if you want to. So you can go to File and click Save As. And this time when you save, make sure you check that you're saving the image, bitmap, PNG, or TIFF, whatever. Anyway, so that's the image. So once you acquire the image, you can then tell the software to take spectra from certain areas of that image. And you do that with these tools up here. So this first button does the X-ray spectra from the entire scan area. The second one does reduced area mode. So you get this little red box. You can draw that on top of a region where you want to collect the spectra. The third button is the point mode. So if you go to point mode, you can then park the beam on 1 pixel in the image. And this would be equivalent to just zooming in with the Sem. The advantage being that you can get a lot of spots covered without having to move around a lot. The other functions, this is like a polygon mode. So this like lets you draw kind of a strange shape on the screen, and then it'll scan the beam inside that area, and so on. The reduced area mode, this I don't believe is active in here. I think this is only active in the mapping tab. But let's just, for now, I'll just show you how this works. So I'll park the beam over here in the carbon, and we're going to come down here, and we're going to clear the spectrum with the paintbrush roller. And then if we say start, that will collect the spectra from that location. And we have our normal peak ID function right here as well. So we can say go. And so now the beam is only in this particular spot. And okay, let's say we're happy with that. So we hit stop. And then we can move the beam somewhere else. Now, one of the things to watch out for here is if I hit start, it doesn't delete the previous spectrum. It just adds to it. So you can get yourself in trouble if you forget to clear the spectrum as you move around. So make sure that you clear the spectrum, hit go, record this spectrum in this particular location. And then if you want to save it, what I find the most useful way to do this is go to Save As. And one of the options down here is going to be the spectrum and image combination. So if we choose spectrum and image, we'll go with bitmap for now, and say, give it a file name. This is going to be like carbon from image tab. So now if we go look at what was just saved, where did I save that? I must have saved that in some weird new spot. File, I probably just wrote into someone else's folder. Save as, yeah, I went into someone else's folder. Oops. All right, EDS training, and we'll do a spectrum and image. And it's carbon from image tab. So now what we'll see is we get the image. So here's our bitmap, and we get the spectrum. Now, one of the things to be careful of is you notice that the crosshair is not preserved in the image. So if you want the crosshair to show you where the signal came from, I don't exactly remember how to get that. So if we say save as, yeah, I don't remember how to get that. So just be careful with that, it's not necessarily going to preserve where your spectra came from. So you might want to, make some notes or do something like that so that you know where your spectrum are coming from. So now if I move my spot over here to the tin ball and clear my spectrum and hit go, now I get my spectrum from my tin ball. And these can be quantified. There's a little Q button right here, so you can quantify, and this gives you your quantification based on the element ID. So I didn't run the element ID, which is why this is wrong. So if we come over here and say run peak ID, there's no calcium or fluoride, it's just tin, okay. And then say quant, and then we get the quant result for the tin. And again, this is hard to save. The easiest way is just to copy it and stick it onto like Notepad or something, and then save it that way. All right, so that's the point analysis with images. One thing you can do is these buttons up here change how this kind of display looks. So if you want, you can use Genesis to acquire images. And I don't know why you do this, because the Sem takes better images than Genesis does. But you can, in theory, have like an image group. So like if you zoom in here, and I click on this quadrant and say collect image, anyway, there is a way to collect multiple images and have them all stacked up in here. Again, these are all features I never use, but it talks about it in the user guide. Let's move on. We just have a little bit of time left. Let's move on to the last and probably the most important thing. Hold on a second. Sorry about that. The janitor came in. Okay, so the probably most important thing that everyone wants to know is how to do high resolution mapping. All right, so mapping is pretty simple. Let's go find an area that we want to acquire a map on. And we're going to turn the mode of operation into the mapping mode. So we're going to go up here to maps and lines mode. And let's look at the whole field of view. And first thing we want to do is make sure your count rate is really high. Maps require a lot of counts to be efficient. So let's make sure we're on our highest possible count rate and make sure everything is adjusted to get us the best count rate we can. So in this case, at 10 kb, we need to be way up here at our max beam count. let's make sure our focus and astigmatism are reasonable. Okay, so if we take a map of this image, we should expect that we'll see areas in here that don't have any tin, and we should see areas over here that do have tin. So first thing we want to do is collect a Sem image. So just like the other tabs, we're going to say collect electron beam image. Okay, and then the next thing is we have to build the list of elements that we want to map. So there's two ways to do this. One is if you've already acquired a spectrum from this area, say in the spectrum tab or the image tab, you can import that data directly down into here. And the way you do that is you go to File and you say Import Spectrum from either the Spectrum tab or the Particle tab. So if I say Import Spectrum from Spectrum, that brings in my last spectrum acquired from the Spectrum tab, which in this case was the copper and aluminum sample. So that's not very useful. If we go back to Spectrum and let's see, we want to get out of the calibration window. How do I get out of calibration? There we go. So if we say clear, collect, peak ID, and I know there's no boron here. Let's get rid of boron. We'll do carbon. Yeah, we can do oxygen, maybe a little bit, silicon, and tin. Okay, so we have our peak list established from the Spectrum tab. So now if we go over to the Maps and Lines tab, and if I say File, Import Spectrum from Spectrum, that brings in that spectrum I just acquired, but it also fills in the list over here for elements that you want to map. So it automatically brings in the carbon, oxygen, silicon, and tin. If you don't do it that way, the other way to do it would be clear your spectrum and hit the little stopwatch, and you can collect the spectrum. And the same tools that you use in Image tab work here. So you can do points, you can do reduced area boxes on things. But anyway, you can collect the spectrum, and then you have to ID, where is it? Here, the peak ID. So you can run your peak ID, put in your elements that you want here, and same idea. So it just saves you some steps. Remember that if you already got the spectra from this sample, you can just import it from the other tab, and you don't have to do it again. Now, let's just say, for instance, we just want to map this whole area, pretty big map. We want to look at our settings here. So we're going to do either maps or line scans. We'll do map mode first. If you want to do a reduced area map, you have to select reduced area mode right here. Live mode just shows you the map as it's being acquired. We don't have WDS or live quant available on here. The SPC button, remember to check the SPC button. If you don't, what will happen is the software records the images as it builds the map, but it doesn't record the spectrum information. And where you want the spectrum information is if you want to go back and reprocess this data later, without the spectrum information, all you're left with is the images. So make sure you click spectrum. These buttons right here just show you different signals. They're like phase map versus elemental map. I'm not going to worry about that right now. And then your map settings, again, you can right-click on this and you can change the various options. So we can do like map resolution of like 256 or 128. I'm going to do like a small resolution so this goes pretty fast. Avoid the temptation to jump up here to like the 1024 or 24.8 resolutions. Those maps look really pretty, but they're going to take you hours to acquire. So don't go with more pixels than you actually need. Let's just see what this looks like at 128 pixel. And then the other things we can look at are the number of frames to acquire. Again, 64,000 frames is probably going to take a week to acquire at these conditions, so be careful here. Let's just do like 16 frames. The regions of interest apply to these elements, so 4 ROIs means it's going to map four elements. And then you see frames on there. And then some of these other options you can look at are like spectrum mapping. You can change some of these things. Scan selected area. The EDS range, it's only going to look out to 10 kV, which is fine. We're only scanning, or 10 keV, things like that. I don't change it. Most of this stuff I never change, but that should be good. So now we're ready. We're going to hit collect map. And the software requires you to tell it the file name. And it's going to apply this file name to every map that's part of this data set. This software has an unfortunate 8-character limit for the maps. So if you're doing a lot of maps from the same sample, you're going to run out of like combinations to name everything. So what I recommend you do is create a folder for each map. So I'll just call this one like map 1. And then inside here, you can call it whatever you want. We'll just say EDS map 1. And we'll save it bitmap, sure, and we say save. So now for each map, for the tin, the oxygen, the carbon, it'll be EDS map 1 carbon, EDS map 1 tin, and so on. This is just a summary of what it's going to save, and we can say OK, and now the map starts up. So as it's collecting data, the quality of each individual map will improve. I told it to only run 16 frames, so it's actually going to stop fairly soon, but hopefully you'll get the idea of this. If I was taking a real map for data I was going to publish, I'd probably run several hundred frames if I had the time for it, because every frame is going to be just better quality looking data. The frame it's on is shown down here at the bottom, so it's on frame 13, now it's on frame 14, so it's almost done. All right, so that's finished, and let's say we want to reprocess this data. So the silicon and oxygen are kind of nothing, there's really no signal there. What we can do is we can click on the carbon and the tin, and I highlight both by holding Control key, and then I can go to process, and I can say, let's see, where do we do this? Oh, sorry. In order to start messing with the data, you have to reopen it. So we just say File, let's say Open, and let's open the EDS Map 1 Spectrum data cube. And so now if I click on carbon and tin and say process, shoot, where is it? I want to do the substitution overlay. Carbon, tin, maybe I have to pick the empty field here. No. I don't know why that's giving me fits here. It should let you combine the two data maps together, and then puts a kind of a combined map right here. I am not. Let's try it again. Open. Carbon, tin, process. Oh, here we go. Okay, so I had to be in the map. I don't know what was wrong with that, but it didn't like it. So anyway, if you reopen the data and then you're looking at it here, you can select multiple maps and you can overlay them together. To be honest, doing some of this is easier in another software package, but you can try to combine everything together. Okay, so let's go back. Let's clear all of this stuff out. We'll say edit, and we'll say clear all, say yes. And we'll go back to our kind of regular display. Here we go. And let's go ahead and acquire, let's see if we can get a little bit better quality map. So let's turn off our external scanning. Let's zoom in a little bit. And let's just see if we can get resolution to see these individual particles. I don't think we will with these settings, but let's see what happens. So these are, how big are these guys? Kind of these smaller ones. They're on the order of about 370 nanometers. This bigger one is about 700. So let's see if we have enough resolution to pick up this sort of scale feature. So we'll do a new Sem image. And let's just say we use the same settings, but let's do more frames. Frames, we'll do like 64 frames. And we'll say collect. Okay, so you can see here that we still have enough resolution to pick up these bigger tin spheres, but we're losing, we don't really have the ability to get these small ones. So, right, if we look at our Sem image, there's a whole little class of small spheres in here that just don't show up at all on the X-ray map. And the reason for that is our accelerating voltage is too high. We're at 10 kV, and that 10 kV is just, it's just too high of a voltage. When the electron beam hits that sample, the beam scatters into a big region, and the resolution of the X-ray map ends up reflecting the size of that interaction volume rather than the size of the electron beam when it first hits the sample. So our secondary electron image has enough resolution to see those small particles, but the X-ray map does not. So let's say we really want to get those little particles to show up. The way we do this is we need to get our accelerating voltage down to the absolute minimum value that will work for us. And the way that you can figure that out here, let's stop our maps. We'll hit stop map, and I'll say end the current frame. What we want to do is take a look at our spectrum data, and we want to look at what is the highest energy line that we care to map. And in this case, if we look at our tin, we're going to map with this tin line right here probably, which is sitting at 3.4 kV, or about. The rule of thumb is that you want to be twice that energy for the accelerating voltage will give you the best resolution map that you're going to get. So if this this tin line is what we're going to map with, it's at 3.45 keV. What that means is that if I set my SEM to about 7 kV accelerating voltage, so double that value, that's going to give me about the best map quality that I can do. So let's try that, and let's see if we can improve our map resolution and see what we can see. So let's go back to our Sem, and we're going to drop our accelerating voltage down to 7 kV. And we're still at our highest beam current possible. We're still using EDS mode. Let's check our alignment. We want to make sure we've got all the signal we can get. We'll check our lens alignment. So to be honest, what I'm expecting to see is that we're not going to get those small particles just yet. The last step that I'll show you is we're going to put the SEM into the high resolution lens mode, and that will be hopefully the final thing we have to do to map those small tin balls. Okay, let me get away from this big tin sphere so we're not getting shadows. Don't want that. Okay, so that looks pretty reasonable. So let's go back over to our software. We'll hit collect electron beam image. And then let's see if we can see some of those smaller features. So we'll hit collect map. We'll do map 3, call this one. And let's see what happens. So hopefully from this demonstration, I'm trying to show you that with SEM EDS, even under the best circumstances, you kind of run out of resolution in your X-ray map compared to what the SEM can see, right? Because the SEM, I can easily see these little tiny tin spheres in here, but on my EDS map, I could really only resolve the big ones, and even then, it's not super clear. Now, some of this might be because my size of pixels is really big. Some of it might be from drift. So let's go into the high resolution lens mode. We'll use drift correction because I want to show you that, and let's see if we can do any better here. So let's stop the map. Turn off that map, and let's go back to our SEM. And I'm gonna, yeah, we're getting some drift. That's not helping. So we're gonna switch over to the immersion mode on the SEM. So I mentioned you can't do EDS on the Nova in mode 1, but you can do it in either mode 2 or mode 3. The drawback to doing it in mode 2 is you generally pick up more background signal. However, you'll see that the improvement in SEM resolution is, I think, worth the extra noise. And let's make sure our image is good here. Now, for any of you watching this that don't really know how to set up the Nova, I would recommend check out some of the other videos we have online that talk about just basic SEM operation of the Nova for doing alignments and astigmatism and things like that. Because you're going to have to be able to get the Nova resolution much better to do this kind of work. You can't rely on it to just be in mode 3 all the time. Okay, so that doesn't look so bad. So let's see if we can in this condition now, if we can resolve some of these tiny little features here. It actually seems pretty stable to me. Let's try it without the drift mode for once, and then we'll turn on drift and see if it helps. So there's our features. We'll hit collect maps again. And we'll do another folder here. now let's see what happens. Take a look while this is running down here at the Spectra. Notice this giant peak that showed up in the middle here that wasn't there before. If I click on it and run my peak ID, which it won't let me while I'm collecting a map, but my guess is it's probably aluminum. And what's happening is that the very high power objective lens is causing some of the electrons to scatter onto the aluminum that is around here, right? This sample is sitting on an aluminum stub. You also see a lot of times you'll see like iron and nickel and things like that, which come from the electron lens itself. So you get a lot more weird background signals when you're running with the high resolution lens mode than you get when you run with EDS mode. But you can see that your resolution, it takes a step up in terms of the quality. And now we're able to see some of these even smaller tin spheres in here. And if I were to measure, let's see, what's the smallest sphere I think I can see in here? It's probably maybe this guy right here, or this one. So if I go to my Sem image, let's measure that one. So this one right there measures 180 nanometers in diameter, and I can see that pretty clearly in the X-ray map for tin. What else? These ones are kind of doubling up, but it looks like we're getting drift problems now. So let's turn on drift correction. Let's see if we can get this any better. So we'll stop the map. Post some of this other stuff. In theory, we'll stop the map. Okay, there we go. Stop the map. Oh yeah, for sure we're getting drift. So drift is definitely not your friend when you're trying to do high resolution X-ray maps. But fortunately, all the modern software has some kind of drift correction module. This one also does. Now, the trick with setting up drift correction on Genesis is you need to have a distinct feature right in the middle of your Sem image. And that's just because the Genesis software is looking for features in that area to do the drift correction on. So what you don't want to do is, for example, if I were to set up my image like this, where I have this big featureless black hole in the center of my Sem image, drift correction is not going to work very well. You want to have something in the middle that's unique. So like if I set it up kind of like this, this should work better. Or even better, let's put this big tin ball right in the center, and it can drift correct off of that. Now, we can also do reduced area mode. Like let's say we don't need this whole field of view. So let's go back over to the Genesis software. And what you want to do is put it into reduced area mode by clicking the reduced button right here. And we're also going to do drift correction. So let's turn on the drift correction module. And let's turn up our, and this is the wonderful joys of using this old software, is that it's buggy and it just crashed. So we have to shut down all of the Genesis programs, which can be a little tricky because if you see here, I've got these little floating remnants of Genesis everywhere. So what you want to do is go into Task Manager, and anything that starts with Genesis or like Gen, so Gen EDS, Gen Part, get rid of all of this. So click on it, say End Process. Gen Auto, EXE, get rid of that. Gen Part, they'll all be under the MC2 user ID, which kind of helps. But this is just really frustrating. Gen Tabs is like the main software. EDAX. Get rid of all this stuff. I think I got, drift shell. We need to get rid of EDAX drift shell. Is that all of them? I think that's all of it. Okay, let's try that again. So we'll restart Genesis. And we'll go to maps. Right, so reduce mode, live, spectrum, turn on drift. That time it opened up the drift shell, but it didn't crash. And then when you turn on drift mode, it'll acquire a new Sem image. Right, and you see here the drift reference is in the middle. I don't think you can move this around. I think that's why I say you want to have like an obvious feature right there in the center. So now in reduced mode, I can draw my small box. Like let's just try to map, let's map like right here. Just see if we can pick up some of these small little guys right there. So in reduced mode, you set the resolution based on the number of pixels in the box, but the pixel size comes from the full area mode. So if you had it in 128 mode, that kind of dictates how big the pixels are in your reduced area mode. I think you can change that though. So when we hit collect, we can upgrade that. So we'll hit collect, map, and then right here. So by default it wants to do just a tiny little number of pixels. So let's increase that up. Let's do like 256 by 256 pixels, which those won't be square. Let's make that a little smaller, 240. Actually, no, the Y should be bigger. Let's make that 256. Let's make that like 240. It doesn't really matter, I guess. We don't really need square pixels. And we'll say OK. And again, we have to make a folder. And we don't need to refresh the reference image. I'm pretty sure it's going to be able to find that big tin ball. So let's just hit OK. And now let's see what happens with our images now. So you can see here's our full screen image. Here's our reduced area Sem image. And then as it's building the maps here, they'll show up in this area. And this should give us the best quality that we're going to get out of here. So I'm just looking while I'm waiting here that there's a question that someone asked that said, would carbon, nitrogen, and oxygen be able to be distinguished? And yes, you can see the difference between those elements. Generally, the EDS software is sensitive to anything higher than carbon. And I don't have a sample on here that has nitrogen on it that I know of, but you can tell the difference between those elements. So as I mentioned, if you turn up the number of pixels in your image, it starts to slow down your maps quite a bit. And this is an example, right? I'm doing 256 by 200 something pixels, and you can see how slow these maps acquire. But if it's done, if I let it run till it's complete, it should be a really pretty map. But then hopefully this gives you an idea of what to expect in terms of minimum resolvable features for X-ray maps. So this this small little window is, let's see, what are we mapping? We're mapping this tin ball. Kind of like this field of view here. And the smallest ones I can see I can see this guy pretty easily, right? That's this particle right here. I can barely make out this particle. It's like right, there's a little fuzzy thing right there, but it's not super clear. So I would question whether that one would be resolvable or not. Maybe if I mapped for a really long time, that would be more obvious. But let's go with this one right here. Let's measure how big that one is. And we're looking at about 125-ish nanometers in diameter. And I think that's pretty typical. Now, one thing that if you want to improve your X-ray map resolution, again, go with the lowest voltage you can possibly get. Now, a tin sample is kind of a tough one because the lowest energy tin line that you can map with is sitting out here at like 3.5 keV. But in a lot of samples, there's going to be an L transition line down here in like the 1 keV range or less, which means that you can go even lower voltage. So if you still use that rule I told you is use twice the accelerating voltage compared to the highest energy line, usually you can get away with like a 5 keV map, and that will get you a little bit more resolution. But I would expect about 100 nanometer diameter particle is about the max resolution you're ever going to pick up in an X-ray map, and that would be under ideal circumstances. So if you need to do EDS mapping on small features like this, like anything I would say like 200 nanometers or less, you might want to consider going to a TEM because making that really thin sample, it limits the interaction volume problem, and now your resolution is not limited by really anything except the resolution of the microscope. So that's really my suggestion is that you should consider about 100 nanometers the best you're ever going to get in terms of a minimum feature size for EDS maps. So this is still mapping, but let's go ahead and stop the map because it's time to shut everything down. So the maps on Genesis, the data gets auto-saved, so unless you tell it to discard the data. So as soon as this thing decides to stop, right? So as long as I say save data, then that data gets preserved. Now you can go back and reprocess those maps. Like for instance, if I say file, why is it still running? Oh, the drift shell is still running. Right, so if I say file and I say open, okay, let's clear everything first, just so I don't do something dumb. Let's say clear. Edit, clear selected, and then we'll say file. We'll open the map we just acquired. Right, and then if I come down here, I have the option of building different types of maps, and I always forget what these are. One of them is the atomic number, one's net intensity, and I think one is like a phase map. Let me just click on one of these and see what happens. So, let's try this. No, that's clusters. Okay, here, the middle one, build maps. So let's, instead of looking at net raw regions of interest, let's try to plot the net intensity map, which will do a background subtraction. And we have to save this again. Let's just call this a net map. Let's say go. And what that's going to do is reprocess the data. And because it's doing the background subtraction now, it should remove a little bit of the noise from those maps. It's not the quickest software in the world, unfortunately. So cleans it up a little bit. Other things you can do is you can do lines from the map. So once I acquired a map, I can click on the line scan, and there's a draw line function here. So if I draw a line across this tin ball, and then say collect, no, that's show line. I say collect line. Because I'm working with the saved data, let me try to do a quantification. Let's do atomic percent. And let's just call it line Save. So this is, as far as I know, this is working off the saved data, not acquiring a new data set. And it brings this up in Excel, which is not terribly useful. But if you plot this out, let's say insert chart. So here's our atomic number, or it's supposed to be atomic percent. So this is probably the tin line here. So we got these two tin balls, and the carbon is the other one. And this kind of gives you an idea of the edge resolution of the map right now. So, right, so that 2 to 3, that's in, I think, what's that distance in? That's probably in, I don't know what that distance is in. I think it's in pixels. Anyway, you get the idea. So you can replot and reanalyze this kind of data this way. So that's everything I wanted to show. There's obviously more you can do here. Again, check out the help guide. Come ask me for questions if you want. But hopefully this is enough to get most people started with Genesis. And I'm going to go ahead and shut down the system. Remember to take it out of EXT/XY scan mode. And then we'll close Genesis. Genesis has a habit of locking up the microscope software, so you might also want to consider rebooting and restarting the microscope server if you've done a lot with Genesis. Just from my experience, that can save the next person some hassle. And we'll close everything over here related to Genesis. And yeah, we'll shut down the microscope. So I look forward to anyone that has questions. Send me an email. My contact info is on the MC² website, or you can come talk to me in person. So I hope you enjoyed this, and have a good evening.